let's see, what to do. Well, since we're getting back into the groove of things, I decided I was going to pick a compelling test question off one of my previous tests and work it. And this kind of has everything. This has Laplace's equation. This has the definition of voltage. This has, at the end, as a bonus question, I think I even put in a question about calculating capacitance. So it ties in with what we finished up with mostly last Thursday. So you recall what happened there is we learned that capacitance is really the ratio of charge separated to the voltage between those charges on two metal plates of any arbitrary shape. And you define capacitance that way. That ratio is always a constant. It depends on the geometry and the material, and usually nothing else. And we worked through an example of how to do that for a coaxial capacitor, which is an inner conductor and an outer conductor with a dielectric in between. Now, truth be told, I don't know of any practical capacitor device, so to speak, that's made that way. It's actually a very useful result, right? Because we were able to calculate through just analysis the per unit length capacitance of that coaxial capacitor. And that's one of the electrical parameters that we studied in transmission line theory. That's what we use to help calculate the impedance of the device, which is important for matching and designing traces. That's what we use to calculate the velocity of propagation. That was one of the things, 1 over square root of LC. So you can see all this esoteric HARP, Nabla's, divergences and gradients and all. It looks very esoteric, but actually has some very practical analytical results. And so I thought that there's this one problem on the test that I like that I'll go through, that'll kind of tie everything together as a review. And then today what we're going to do is start talking about currents. We're going to leave the world of electrostatics and get into magnetostatics. So here's a question, word for word, as I put it on the test from 2000 whenever. This is a question primarily about Laplace's equation. Remember what Laplace's equation is. It's the Laplacian of voltage is equal to 0. Of course, that would have been on the back of the test. And this is for charge-free space. And the problem goes something like this. Two semi-infinite conductive plates are joined at the z-axis and held at 0 and V0 voltage as shown in the diagram. So the problem looks like this. We've got, let's draw our right-handed coordinate system, x, y, and z. And of course, semi-infinite plate, so basically everything, there's in the xz plane, there's an infinite plate. And a semi-infinite plate, half that plate is over here. And it's a piece of metal held at 0 volts. And then this other plate, on this other half of the z-axis, but still in the xz plane, is at V0 volts. So you can imagine there's a really nice thin insulator in the z-axis that keeps current from rushing from here to here. Otherwise, these are, you think of this as being supplied by a voltage source two separate pieces of metal being held at a potential difference V naught. And these are semi-infinite, which means this goes on and on and on. So you kind of get the geometry of the situation we're talking about. Two plates joined together, different voltages. And there's several parts of this question that are discussed. And we'll do all of them. Part A says, use Laplace's equation to derive the result voltage as a function of rho, phi, and z. So obviously we're using the spherical coordinate system to describe a point of observation, is equal to V naught over pi, absolute value of phi. For the region negative pi is less than phi is less than pi. So basically what this says is that there's a linear taper in voltage as I swing my point of observation. It doesn't depend in R and it doesn't depend in Z. As I swing my point of observation around until I get to here where it's a peak. And then because that absolute value sign, if I swing it the other way into negative phi, remember phi is always measured from the x-axis. As I swing it negative, it also linearly tapers up to V naught. This makes sense. It's a symmetrical problem. So the way that we solve this, so I give you this, right? I say prove that that's true. So here's one way of doing it. We have a Laplacian of a voltage. And here, remember, we're expressing this in terms of cylindrical coordinates. So that means that you just can't take the regular Laplacian second partial derivative with respect to x twice, second partial derivative with respect to y, second partial derivative with respect to z, add them up, just like you do in Cartesian coordinate system. Rather, you've got to operate only on using the formulas in the back of the textbook, or in this case, in the back of the text which I supply you. So if you look at the definition of the Laplacian of something that's only going to vary with respect to phi, because this problem looks the same if I move away from it in radius or I translate the observation point with respect to z. Only angle is only the angle is present in the solution that I've given. So we only need to write the part that depends on the partial derivative with respect to phi, because there is no dependence with respect to z and rho. So let's write that down. If I look at the back of the book, I can cheat, or the back of the test. I find that the Laplacian of v is equal to 1 over rho squared partial derivative of v with respect to v, second partial. And that's it. That's my only non-zero term. So according to Laplace's equation, that must be equal to 0 in the charge-free region in between the plates, on either the right or the left-hand side of the plates. So now I just have to solve this differential equation. And this turns out to be a pretty easy one to solve. First of all, I notice I can multiply through by rho squared. Times 0 is still 0. So that's a pretty easy partial differential equation to solve. I just integrate it once. What do I get? I get the first partial derivative with respect to phi, and that must be equal to some constant. I'll just call it C2 for now. I integrate it again. What is it equal to? C2 times phi, because now I've got constant. Integral of a constant with respect to phi is a constant times phi. And I got to add another constant. How do I solve the constants? Well, I just need to enforce my boundary conditions. When phi is equal to 0, this evaluates to just C1, and I know C1 must be 0 because when phi is equal to 0, I'm on that 0 voltage plate, right? And when V is evaluated at pi, I get C2 times pi, and that must be equal to, well, plus 0 because C1 is already 0. That must be equal to V naught. So there we already know that C2 is equal to V naught over pi. Plugging those back into my original formulation, I get V as a function of rho, phi, Z is equal to V naught over pi, that's my C2, times phi, and I can put an absolute value there because this is valid the way I've constructed it for this side of the half space, and of course if I go, the other side should be symmetrical in its nature as well. So when phi is negative, I should get the same linear taper up. Yeah, Cameron.
I'm kind of lost at what you did here. You took the first derivative of V and you got C2, which I guess in this case, if you actually took the derivative of V, it would be V naught over pi.
Well, this is, for really simple partial differential equations like this is a simple way to solve it. You say, this is the derivative of V with respect to phi taken twice, right? And that derivative is 0. So if I integrate both sides with respect to phi, I get this. In other words, if I take the derivative of this with respect to phi, I get 0. If I take the derivative of this with respect to phi, I get the second derivative. And then I just repeat. Rinse and repeat.
Also, if you plug in pi for V, would it be C2 pi plus C1?
Yes, it would be C2 pi plus C1, but C1 from the previous step was 0. So I should have written that down. Plus C1, but it's going to 0.
Why was C1 0 again?
Because for this generic form, when we evaluate phi equals to 0, then V is equal to C1. But that phi equals to 0 corresponds to anywhere along this 0 voltage plate. So that's the first boundary condition we're enforcing, and that implies that C1 must be equal to 0. Remember, if you have a second order partial differential equation like this, you're going to need two different boundary conditions to solve for it of this simple variety. Say, that wasn't too bad, was it? Is everybody getting an A so far on this test? No?
Is one plate on the x-axis, one plate on the y-axis?
No. One is on. They're both on the XZ plane. One is over here. The other is 180 degrees around. Kind of hard to tell from the board diagram, but so you think of it as this is my 0 plate, this is my other plate, V naught plate, and they're just joined like this. And presumably there's a really good dielectric right here that insulates it. Because all good engineers know that if you put 100 volts or something, 2 plates, and then you touch them on the edge, that they're going to conduct at that junction. Yes? Could you speak up?
Why did you multiply phi for the final answer up there?
Why did I multiply phi?
Took the magnitude of it.
The magnitude of phi. Well, so I solve for C1, that was 0. I solve for C2, that was V naught over pi. So when I plug those back in, that gives me my final answer. And that's valid for this front half of the plane. And I can, we know by symmetry that if we go on the other side of the plane where phi is negative, I should get the same answer. So we don't have to redo all that work. That's a perfectly acceptable answer at that point. Yeah?
So I guess for the diagram, that's how you
knew that phi of 0 would be 0.
That's right.
Okay.
Yep.
So I couldn't figure out I guess if you're given the diagram, you can figure out the
Yeah. So, you kind of come up with this generic solution which says that, well, I know that it's going to, for this particular type of geometry, with these symmetry assumptions I've made, the voltage is going to linearly increase. It's going to start at a value, and it's going to linearly increase to another value. We just got to get those constants of proportionality and constant offsets pinned down, and that's what the boundary conditions are for. Has everybody had differential equations here already? Okay, cool. Go, Cameron.
Also, just to kind of confirm, when you were drawing the diagram,
Yes.
you have a plate coming down on the x-axis meeting at the z,
right.
origin, and then coming down on the y-axis meeting at the z origin.
No. There's nothing on the y-axis. The y-axis is perpendicular to both plates.
Mm-hmm.
They're side by side.
So there's just two plates coming in.
Yep.
Okay.
Yep. Together they form an infinite sheet on the xz plane.
Okay.
You said phi is always a function of x, right? We always measure it with respect to the x-axis, right?
That's right. That's right. Phi is how many radians you have traversed from the x-axis in your point of observation. So this problem winds up to be almost trivial looking when you solve it in the cylindrical coordinate system, which is why we kind of picked it. This works better in this coordinate system rather than the Cartesian coordinate system. Okay, let's try. Oh yeah, okay. Let's try the next question. Use the voltage in A to show that the electric field for this problem is E vector as a function of rho, phi, and z is equal to negative V naught over rho pi in the phi hat direction for phi between 0 and pi, and positive V naught over rho pi in the phi hat. When phi is negative. So how do we do that? Well, we know from this class that electric field is negative the gradient of V. But again, we can't just stick our partial derivative with respect to x, stick it on the x, and so forth, that we use when we use this as a Cartesian operator. We've got to use the cylindrical coordinate operator. So we know what the voltage is already. We just need to figure out what that proper operator is. So looking in the back of your EMAG text, if this was a homework problem, or looking in the back of the test, if it was a test problem, what you would find is that the gradient minus the gradient of anything with respect to spherical coordinates, if this is only a function of phi, I only have to worry about the phi component, it turns out. That's the only place where a derivative with respect to phi shows up. All the other terms are going to evaluate to 0 because they've got partial derivative with respect to rho and z. My voltage that I found over there doesn't depend on those. So there's always going to be 0. So here, I get 1 over rho partial derivative of v with respect to phi, stick it on the phi hat. Well, I've got that solution over here. This is the partial derivative with respect to phi of v naught over pi. When I'm in this region, it's just going to be positive phi. When I'm in this region, I've got an absolute value sign in my voltage function. So when phi is negative, I can really just write this as negative v naught over pi. So this is for phi greater than 0. This is for phi less than 0. Everybody understand how I did that, right? Either way, this is a trivial derivative to take. I'm just differentiating with respect to phi. My final answer is going to be, well, if I differentiate this constant times phi with respect to phi, I just get the constant. So it's going to be minus v naught over phi, pi rho, the constant divided by my rho. Can't forget that term. Stick it on the phi hat. And when I'm over here, I've got a minus here. That's going to cancel with that minus sign. Otherwise, I get the exact same term. V naught over pi rho, stick it on the v hat. Does that make sense? There, 100% so far. We just got 100% on that problem. It's pretty easy. All I had to do was take a derivative. I just needed to know which kind of derivative to take. Any questions so far?
On the first derivative where you did phi greater than 0,
Yeah.
should that one be the negative one?
I don't think so, because when phi is greater than 0, absolute value of phi is the same thing as phi, right?
Yeah.
So I just plop a phi instead of an absolute value of phi. So I take the derivative of that. That's v naught over pi. I got a negative out front here.
I was like,
Oh, yeah. There's a couple negatives floating around, so. Okay. Let's see what the next question has. Ooh, this one gets a little tougher. On our plates, not that tough, but just a little bit tougher. This asks, what is the surface charge density on the plates? On the plates. And there's a couple hints here that I gave on the test. Hint number 1 is this following relationship. The volume charge density as a function of 3D space is equal to the surface charge density as a function of rho and z divided by rho with a delta function. So in other words, if I want to describe the charge, say, on this particular plate as a volume charge density, it's really a surface charge density with a delta function with respect to phi. Because all the charge is actually compressed to this one plane. It's 0 elsewhere. It's infinite. The delta function is infinite. And really what that means is we're just taking that volume charge that has coulombs per meter cubed and compressing it onto a surface charge that has coulombs per meter squared. The other hint that came along with this was actually in the first statement. I'll reiterate it over here. In addition to that piecewise solution for the electric field that I gave the following result as well. Electric field could also be written as 2v naught over rho pi times 1/2 minus the unit step function with respect to phi. And all this does really is this turns off when phi is negative. So I really just get v naught over rho pi. And and this is on the phi hat unit direction. And if I am on positive phi, then this turns on. I get 1/2 minus 1/2, minus a 1, so I get minus 1/2. So I get basically V0 over rho pi with a negative in front of it. So does everybody see that this is really just the same thing as this over here? Just another way of writing it. I put a little jump up to denote that the field is pointing into the swirling around and pointing into the semi-infinite plane over here, and then it quick flips direction when you cross that plane and go to the other side. Now, an abrupt change in field like that, where all the field tends to be pointing in, what is that? Sounds like sourciness. Sounds like sourciness. In fact, we know that D field is equal to epsilon. I think this is a free space problem in the formulation, so we'll just use epsilon naught. I could have packed it with dielectric material. Times E, my E field. So I could write this as 2V naught epsilon rho pi times 1/2 minus unit step. Stick it on the phi hat direction. And I also know that the divergence of D is equal to the volume charge density. The sourciness of your field is equal to charge. And it turns out that this will tell you, using this relationship, you can tell exactly how much charge is on that plate. So let's see. What's it going to be? I look at the back of the book, and I note that the divergence of E is really epsilon 1 over rho times the partial derivative of the phi component of electric field with respect to phi. And all the other terms in the divergence are 0 in cylindrical coordinates when something is only a function of phi like this. So let's see. Let's take the partial derivative of my E field with respect to phi. Well, I got a constant here, 1/2 times this other constant. Derivative of that's always going to be 0. What's the derivative of a unit step function? A delta function, that's right. That's right. So if I just treat this as a constant, what I can write this then is 2V naught rho pi. I got a minus unit step function. That's a delta function. So I got a minus sign. I'll just bring that out here. And then I'll have a delta like that. And that's what's equal to volume charge density. Oh, but wait. I had a helpful hint. I can convert a volume charge density to a surface charge density using that convenient formula. So really, grouping my terms, delta phi, I got a rho, everything else is surface charge density in that expression. So it's going to be minus epsilon naught 2 V naught, and let's see, and I get a rho squared and a pi in the denominator. I get a rho squared from here and here. I take one of them out, so I just get a rho here. So this is my surface charge density. And let's see, I need a 2. I got a 2. I got a 2. So that's it. That's my surface charge density. That's on the 0 voltage plate. On the V0 voltage plate, I just flip the sign, right, because it's a symmetrical problem. I got this much charge, surface charge, on that first plate. And notice the magnitude. As I put more voltage on that second plate, as the difference between the two voltages increase, so does the amount of surface charge. Also notice that it tapers. The surface charge tapers away as I increase the voltage, increase the point of observation with respect to rho. So I move away from the z-axis, and my charge density on the plate tapers out. Yeah, tapers out this way. The polarity changes on the other side, on the other plate, and that tapers as I move away from the z-axis as well. So this, in a way, is kind of a very bizarre-looking capacitor, right? Normally, when we think of capacitors, we take the plates and we put them like this. This is the most useful configuration. But sometimes you can have capacitors like this. You wouldn't necessarily want to build an electronic component capacitor, like a discrete capacitor like that. It's kind of hard to control the values, and there's an influence of what comes nearby in this configuration on the actual capacitive value. Where might you want to use where might a capacitor like this show up of this type of geometry? On a what?
On a circuit board.
On a circuit board, yeah. Yeah, for example, you could have, and this was the next bonus part of the question, was to find the capacitance using this approximate result of two coplanar strip lines. So coplanar strip, you've got circuit traces, maybe like a thin dielectric that doesn't really influence the propagation very much. But you've got two plates that are side by side with relatively little intervening space. And you can actually use this result and the attendant charge densities to estimate the capacitance. Yes?
Dr. Durgin?
Yes.
This is Bill in Savannah.
Oh, okay.
Could you explain your part C again real quick? Just go through. Why did you use that hint, and why did you rewrite the electric field in a manner to have a step in it?
Oh, okay. So this was given in the problem statement here. To go back to our problems to see, these hints were actually given in the problem statement. If you look online, I said you could write the E field in either this form or this form. And then as part of the hint to this problem, I said, well, if you've got a volume charge density that's concentrated on one of these semi-infinite half planes in the cylindrical coordinate system, you can write it as this. Surface charge density collapsed onto a single phi plane, so to speak. And so those were given. So I know that if I get a problem like this, what is the surface charge density on the plates? I know field. I'm being asked for charge density, so immediately think the divergence theorem, because that's what that tells us. It says we know the field, we want the charge. It's the opposite of Coulomb's law, which says we know the charge, we want the field. And so I'm going to have to apply the divergence theorem, which says if I take the divergence of epsilon naught times E field, I will get something that's going to be equal to my volume charge density. And in the end, this hint was here just to help the student. I wouldn't expect anyone to know this, but to recognize once you got to this step to convert it into a surface charge density, if you were so inclined. But I do expect you to be able to take the divergence of a simple function in cylindrical coordinates. How do you do that? Well, you take the E field that I gave you in the problem, which basically describes this electric field that's swirling and pointing into the 0 voltage plate, and it tapers as I move away from the z-axis. And when I do my divergences, I find that my volume charge density has this mathematical function. And here what I'm doing at this point is just using my relationship to put it into a more physically meaningful result. Now this is a purely mathematical result. I take the divergence of this thing that has the unit step function, and I get this. So what? Well, let's interpret what we're doing. If I put it like this, then I can treat this as a surface charge density And in fact, at this point, you could actually double check your result. You could set up a Coulomb's law integral with this surface charge, and you could get E field. And if it was the same E field you started out with, you knew you did the problem right. Oh, yeah, Cameron.
So, I'm going back to where you have the delta dot the D field equals rho V. So you just took the first top part of the equation where you have just the D field, and you differentiated it just over the phi vector.
That's right.
And that's where you got the bottom portion?
Yeah, that's right. So if you were to look at the back of the book, it might be helpful to write the whole thing out. The divergence of a vector in the cylindrical coordinate system looks something like this. One over rho, partial derivative with respect to rho, rho d rho. The rho component of d field times rho, partial derivative with respect to rho divided by rho. I didn't write this, though, because there is no rho component of the d or the e field. There's only a phi component. The money term in this is actually this. 1 over rho, partial derivative of the phi component of d with respect to phi. And then there's also this partial derivative of the z component of that vector field with respect to z. That, of course, is also 0 in this problem. So I recognize, based on the solution form that I've given, I don't have a rho component of my vectors. I don't have a z component of my vectors. I really only need this. That was the thinking behind that.
Yeah, okay, I understand that. So when you did that, and now you have the next part of the equation where you have the volume charge density. What's the delta phi? No, the next part. Delta phi over rho, and then the whole rho s section. Yes.
Yeah,
What
yeah.
did you come about that? Did you just rearrange?
Yeah, so I substituted. This was my phi component of rho. Let me see. So this is my 1 over rho partial derivative of phi with respect to phi. That was this is the next step. And I plugged that into here. Or, yeah. This is my phi component.
Oh, okay, yeah.
I plugged that into there, took the derivative, and this is what's left over.
Okay.
I think I might have overwritten a step there. And this is sort of like the messy result, the messy mathematical result that when I look at it, it doesn't mean anything to me. But when I rearrange it, and I call this a surface charge density that's collapsed onto that phi plane, now it starts to mean something to me. Oh, I got negative charges. They're spread out all along the plate, and they taper. They fall off 1 over rho as I move away from the z-axis. Yeah?
I think he just asked what I was going to ask, but you just took the derivative of what's in the bracket.
That's right. This is my phi component of d. I took the derivative with respect to phi and divided it by rho. So if you do that algebraically, this should become this after that operation.
Oh, so then that's fine.
Yeah.
Okay. I think that was the same 1 over rho out there. Crystal clear, right? Crystal clear. Okay, let's take a look. We had one bright fellow point out that, hey, you could use this for this kind of problem, right? It's not a semi-infinite plane, but if these are pretty close together, then I could use this similar field solution to solve for it. If I wanted to draw the equipotential lines, for example, let's say this was at 0 volts and this was at V0 volts. Well, in our problem, let's say this was 100 volts. Let's put some numbers on this. So this is 100 volts. 50-volt equipotential line would go right through the middle there. If these were infinite, semi-infinite plates on a circuit board, and we're looking at the cross-section, keep in mind, they go up for infinitely in this direction into the board and away from this line that I've drawn. If these are semi-infinite, then I know that there's going to be 25-volt potential line there and there, 25-volt potential line there and there. And in reality, when we move to these types of plates like this, thin metal traces on circuit boards that have a gap in between there, well, our equipotential lines look more like this. So to solve this problem, we could use that solution as an approximation. It's a pretty good approximation because the area through here, the charge density across here and here, the field distribution here will be pretty similar. Pretty similar. Only on the edge would you see a little bit of deviation. And so that's one of the questions that the bonus question was actually asking. How do you calculate the capacitance from this and come up with an actual result for this? Now, that's one example of where to use it. Where else might you use a capacitor like this? Let me see. Blanca, what are you doing over there?
I'm checking something on my phone.
Oh, is that an iPhone?
No, it's an Android.
An Android? Is it touch screen?
Mm-hmm.
How do they sense the touch pads?
Heat?
Yeah. No, not heat, not heat.
That's what you do.
Yep, electrostatic capacitance between two things that look exactly like this. The way that they make the screens, they take some glass and they have tiny little translucent pads on there. And there's capacitance between each of these junctions that you can sense. And so what is the capacitance when there's no finger near it? Well, you have free space, and you can calculate it, as we're about to calculate it on the bonus problem of that particular test. As just modeling it with two pieces of metal side by side in air. Now, of course, these can't interfere with the screen itself, so they make this out of a special conductor. Usually it's indium tin oxide, ITO in the industry lingo. And it is optically transparent, but it conducts at DC pretty well, which is usually those two things are mutually exclusive. It's actually very hard to find a substance that behaves like that. So you can see through it. It's invisible. But if you take your conductive finger, this is a representation of your finger. Could you hold up your finger, please? Thank you for holding that finger up. Good. She's got nice nails, and she's got a nice finger there. And she brings the finger close in. It's a conductive finger. And now it's like two parallel plate capacitors in series. We could calculate that too if we wanted to. That's easy. So you can see that you change the configuration, you change the capacitance in that area. And by selectively analyzing with test currents and an A to D sampler on a microcontroller, you can pull out the instantaneous capacitance between any pair of capacitors on the screen and sense, oh, is that finger getting close? Is it moving away? Oh, yes.
What's the lifespan of capacitors? Because I've had a phone before that, like, after a couple of months, the touch screen stops working as effectively.
Oh, that's a good question. I don't know. My one guess, the question is there a lifetime to those types of capacitors? And if I had to guess, and this is purely a guess, I know that ITO is a decent conductor, and it's pretty resilient over time. This is what you also coat the front part of solar cells with, So if you think about it, you need to metallize both sides of the solar cell, but one of those is better let in sunlight, right? If you put ITO on one side, that's really the first widespread use of it. But I also know it's a brittle conductor. So if there's a lot of mechanical pressure deforming the surface, depending on how it's manufactured, you can actually make invisible breaks in the material that open circuit the connections. I don't know. Does anybody else have any other secondhand experience with this, or read some sort of article on the internet? Yeah.
Just to be clear, most of the touchscreens are not capacitive touchscreens. Before like 2 or 3 generations of touchscreens were all, I don't know what material they're made of, but they're not capacitive.
Are the current iPhones and all, are they capacitive?
Yeah, they're capacitive.
Okay. What about the Droid one? Is that thermal?
They're better, so they're probably not.
Is it what?
Whatever's better, Droid is.
That was a shameless shill. Yeah.
Well, Samsung just came out with a flexible smartphone. The entire thing was big.
Are you talking about the one that's like one thin piece of plastic and just like it has the stuff in it?
Yeah,
It's like the whole phone. You can like bend it in your hand and like do action by twisting the phone in certain ways.
That's pretty wild. I'm not sure if I would trust the average consumer with something like that.
But if with that sort of touchscreen, you couldn't have the brittle plates. Like
Yeah.
describing.
So how do they do that?
Sony came up with a touchscreen where you don't even have to touch the screen. It just senses your fingers.
Like nearby.
Yeah.
Is that one capacitive?
I don't know. But it's already there and it's already on.
I don't know if I'd want that either. I like to drag the finger across the screen type of feel. I tell you, too many inadvertent like bloopers on your text messaging if that happens, right? You got to get used to it, I guess. It's all what you get used to.
We don't have buttons anymore. No, we don't have a screen.
So anyway, that's another use. So let's go ahead and finish up the problem, just so that you can go home and brag to your parents that you now know how to calculate capacitance touch screens on iPhones. So remember, capacitance, this is find the capacitance of that scenario over there, where I've got 2 traces parallel with a little bit of gap separating. These are width A apart, each of them, and they're separated by a distance B. So capacitance, per unit length capacitance, if this was a transmission line, would be the line charge, the total amount of charge on those lines, divided by the separation voltage. And that's going to be 1 over V naught. The integral, so how much charge separated? Well, I know that positive charges are going to go over here. They're going to be tapered as I move away from the center. And negative charges are going to be put over here. That's going to also taper. It's a symmetrical problem. So if I just look and integrate across A here to figure out what is the total amount of charge per unit length in this transmission line, that will get me the Rosabel that I need to find per unit length capacitance. So I got to integrate, and remember, I called this my origin. So my integration is going to be from B over 2 to this point over here, B over 2 plus A. Or I should probably do it this way, but I just picked to draw it that way. I'm going to start here. I'm going to integrate across here and pick up all of the charge components. Rho sub S d rho. What rho? I'm integrating with respect to the rho axis because the way I've drawn it here, if I adapt it to my problem geometry, I got Z coming out of the board. Rho is the distance away from Z. So I'm in like basically the phi equals pi half plate. Well, if I approximate my surface charge density with the same expression that I had over there, and on that positive plate from the previous problem, we get epsilon naught to V naught over pi rho. V naughts cancel because they're constants. I can take these constants out of the problem too. I get 2 epsilon naught over pi. I cannot take the rho out because that's what I'm integrating with respect to. The integral of that, of course, is the natural log of rho, and I evaluate it at these limits. My final answer is 2 epsilon naught over pi, natural logarithm 1 plus 2a over b. That's the per unit length capacitance. Units of farads per meter. If we wanted the total capacitance of maybe 2 plates on a touch screen, for example, we just have to multiply by the depth, however far these came out. And that would give us an estimate of the capacitance that way. So you'd multiply by the depth factor. And then you'd figure out, you'd be able to calculate as an engineer exactly how much capacitance exists between those 2 plates. And then you could do the same thing with the finger present and adjust it so that you can detect the presence or the absence of a finger. Yes? No. Oh, how did I know the plus was on the left, the minus was on the right? Well, the way that I drew this was kind of a little quirky. So normally, let's draw our coordinate system here. I've got x, I got y, and that means that z's got to come out of the board if it's a right-handed coordinate system. So this, of course, would be phi equals to 0. And this one over here would be phi equals to pi. And the way that my solution was written, this was at 0 volts, this was at V naught volts. This had negative charges on it, this had positive charges on it. I just kind of picked the one that had the positive charges on it. It doesn't matter because regardless of which plane I pick, I'm actually just integrating along the rho axis. It's the same exact integral. If I were to change the sign here, I'd also have to take into effect that I reversed the polarity of my voltages, so I'd have a minus there, and they would have canceled. If you ever get in real trouble on your test and you come up with a negative capacitance, just take off the negative sign, because you probably just flipped your polarity. If you can't find where you flipped your polarity, just take it off anyway, and hopefully the instructor won't notice. Because you know there's no such thing as negative capacitance. Any other questions? Okay.